welcome to this college algebra video on basic matrix operations. So to start with, let's talk about a basic concept here of equality. What does it mean exactly for two matrices to be equal? Well, first of all, they must have the same dimensions. So I can't have a 2 by 3 matrix equal to a 5 by 7 matrix. They have to have the same size, and then I can compare the elements in all the corresponding positions. Now, elements in those corresponding positions, they must all be equal. So as I look at the example here on the screen, the upper left position must equal the upper left position. So the variable a here must equal 10. The lower left position must equal the lower left position. So for negative 23 to equal 23b, b must equal negative 1. The lower right position must equal the lower right position. So c must equal negative 8. I also see here a 3x in this middle lower position. That 3x must be equal to 12, so x must equal 4. And this upper right position with 2y plus 5 has to equal the upper right position in this other matrix. And for 2y plus 5 to equal 105, y would have to equal 50. Well, with that out of the way, let's move on to some more interesting operations here. So every time we learn a new number system, we want to learn how to do the basic things like add, subtract, multiply, divide. Well, it's no different with matrices. Matrices are kind of their own unique object in mathematics, so it'd be nice to learn how to add them, subtract them, multiply, divide them. So let's start with addition. First, a rule for addition: both matrices must have the same dimension or else addition is undefined. And addition of matrices will work just about the way you would want it to work. We're going to take corresponding entries and add them up. So the upper left plus the upper left. 9 plus 12 gives us 21. The upper right plus the upper right. Negative 6 plus 20 gives us 14. If I add 4 plus 7 in the lower left position, I'm going to put an 11. And 15 plus 0 gives me 15 in this lower right position. In our second example, again, we're just going to add corresponding positions, and our answer matrix should wind up the same size as both of the matrices that we're adding. So our answer matrix will be a 2 by 3 matrix, 2 rows, 3 columns, with the entries 9, 1, 5, 16, 0, 13. And you can double check that to be sure I've added all those positions correctly. As we move to our third example, I see that there's a problem here because I could add the upper left to the upper left and add the lower left to the lower left. But does this negative 6 add to the negative 4, which would be the next position over? Or does negative 6 add to the 15, which would be the upper right? The problem here is that these matrices don't have the same dimensions. This one is 2 by 2, this one is 2 by 3. And without the same dimensions, we cannot add these things. There is no solution. The next operation we're going to talk about is called scalar multiplication. And it's called a scalar multiplication because we're going to multiply an entire matrix by a single number. That number out there, we call it the scalar. So the way this works is I'm going to take that scalar, that number out in front of the matrix, and multiply it times each entry in the matrix. It's kind of like a superdistributive property. So in this instance, I'm going to take the 6 times the 3, 6 times 5, 6 times negative 10, and also multiply the 6 across the bottom row, 6 times 6, 6 times negative 3, and 6 times 8. And we'll wind up with this new matrix, 18, 30, negative 60, 36, negative 18, 48. So let's try a little bit more complicated example. First, we're going to find 3a. So this is what scalar multiplication might look like. 3 times a big capital A, standing for matrix A. And we're also going to find 2 times matrix B. So the scalar 2 times the matrix B, and then we'll see what 3A minus 2B is, and that'll give us a chance to see how subtraction works with matrices. So first, 3 times A, well, again, just distribute that 3, multiply it times every single entry in there, and we're going to wind up with 360, negative 393, 6, negative 312. So we're still following the same rules of positive and negative multiplication that we have in the past, just now doing the multiplication times 9 different entries. Next, let's figure out 2b. So I'm just going to take every entry in this matrix, multiply it times 2. So doubled all these numbers would be 4, 2, 6, 2, 0, negative 4, negative 6, 8, 10. Pretty straightforward process. Now, if I want to do 3a minus 2b, here's what I do. I'll write it as 3a plus negative 1 times 2b. So there's another scalar that I could multiply into matrix B. So what I've done is I've taken the matrix 2b that we had on the previous page, and I multiplied all the entries times negative 1. It changes all those signs. Now it's just as simple as adding. 3 plus negative 4 will give us a negative 1. 6 plus negative 2 gives us 4. 0 plus negative 6 gives us negative 6, and so on. Do the same for the second row, same for the third row. So as we've seen many times in the past, subtraction can simply be thought of as adding the opposite. But the opposite matrix means turn every single entry to its opposite sign. Well, so far, hopefully all of these operations have been pretty easy. Addition, scalar multiplication, subtraction even is not that difficult. But there's another kind of multiplication we need to talk about. This is the product of a matrix times a matrix. And the process is a little complicated, so I'm going to start out simple and we'll build our way up to more complicated. First thing I want to teach you how to do is multiply a 1-row matrix times a 1-column matrix. Now, in order to do this, our row has to be the same length as the column. So I can't multiply a row that has 4 elements times a column that has 7 elements. They both have to have the same number of elements. I'm just going to number them 1, 2, 3, up to n. And so to do this multiplication, here's what we do. We multiply the first element of the row times the first element of the column. So A1 times B1. We take the second element of the row and multiply it times the second element of the column. And as we do this multiplication, we're going to start adding up our answers. A1 times B1 plus A2 times B2. Then move on to A3 times B3, and continue all the way until we get to the last element of the row times the last element of the column. And you can see why the row length needs to be the same as the column length, because I don't want to run out of numbers in the row before I get to the end of the column. And I don't want to get to this last number in the row and not have anything left to multiply by in the column. So my last part of this answer is AN times BN. And I add all of these things up to get a single number. So when we multiply a row times a column, we get a single entry in our matrix. If we just start with a single row and a single column, our matrix answer is just going to be a single number. So let's try a few of these. Seems pretty simple, but let's kind of keep working our way up here. We're going to start with the row 37 times the column 410. So I'm going to multiply the 3 times the 4, first number from the row, first number from the column, that gives me 12. I'm going to multiply the 7 times the 10, that gives me 70. Add up 12 and 70, and we get the single number 82. Let's try a little bit longer row and a little bit longer column. Multiply 2 times 4, get 8. Negative 3 times 5, negative 15. 5 times 7 get 35, but I don't have 3 separate answers. I want to add all those up. 8 minus 15 plus 35 adds up to 28. So this single row times single column gives us a single answer. Well, what if the matrix is bigger than a single row and a single column? What if I have a single row matrix, but my other matrix has 2 columns? Well, the first step is going to be to multiply the first row times the first column, which we already did. We saw that that answer comes out as 28. But then we take that first row and multiply it times the second column. This will finally get us a second part to this answer matrix. 2 times 10 is 20, negative 3 times 3 is negative 9, 5 times 6 is 30, 20 minus 9 plus 30 gives us 41. Well, let's keep making this more complicated. What if I have 2 rows, 2 columns? Well, the first row times the first 2 columns is exactly what I already had before. So I should still have those same 2 numbers, the 28 and the 41. But now I have to do something with this second row. The second row, 152, is going to have to multiply times the first column and the second column. And that'll give us 2 more parts to our answer matrix. So I'll do 1 times 4 plus 5 times 5 plus 2 times 7. 4 plus 25 plus 14 adds up to 43. And finally, I have to do the second row times the second column. 10 plus 15 plus 12, and we get 37. So as my matrices that I'm multiplying get bigger, it's possible for my matrix answer to get bigger. Now let's take the same 2 matrices and multiply them again, this time in a different order. Now you'd expect that if you multiply A times B or B times A, you should get the same answer. That's the way it's been for all numbers in the past. Let's see if that's true here. So I have to go a row times a column. We always do a row on the left and a column on the right. So I'm going to multiply 4 times 2 and 10 times 1. That gives me 18. Wait a minute. 18 is not 28. These matrices do not have the same thing in the upper left entry. 28 is different from 18. These must not be equal matrices. Well, now I have to do the first row times the second column. Negative 12 plus 50. That gives me 38. I don't see a 38 up here either. So both of these numbers are different. 38 is not the same as 41. And wait a minute, I still haven't even done the first row times the third column. That's going to be 20 plus 20. So I get a 40 here. So my first row has 3 entries, not just 2. Yeah, this thing could not possibly be equal to this one. It's not even the same size matrix. Well, let's keep going. Second row, first column. 5 times 2 is 10 plus 3, that's 13. Second row, second column. Negative 15 plus 15, well, that one came out to 0. And second row, third column. 25 plus 6 is 31. We're not done yet. We got to do this third row times all 3 columns. 14 plus 6 gives me 20. Negative 21 plus 30 gives me 9. And 35 plus 12 gives me 47. So when I multiply these matrices in a different order, I get a different answer. This is different from any other kind of multiplication we've ever done before. With any other kind of numbers we've ever seen, multiplying the order really didn't matter. 7 times 5 is the same as 5 times 7, but with matrices, we'll say that matrix multiplication is not commutative. That means we don't necessarily get the same answer if we multiply in a different order. A times B is not necessarily the same as B times A. All right, one more thing to try here. We're going to try to multiply this matrix times this matrix a little bit bigger. I wonder what we'll get. So I have to multiply the row times the column. 2 times 6 is 12. Negative 3 times 4 is negative 12. And 5 times, wait, 5, wait, there's nothing to multiply the 5 times. I mean, I just write down 5? No, there has to be the same number of elements in this row and the same number of elements in this column. If I don't have a third element in that column, I cannot multiply these things. So I'm not even going to attempt to multiply these if the dimensions aren't right. So there's no solution for this thing. But why are the dimensions not right here? I mean, for adding this worked perfectly fine as long as they had the same size, we could add. But for some reason now we cannot multiply these even though they're the same size. Well, again, the problem is the row length and the column length don't match. Let's look back at all of our previous examples and see why it was possible to multiply those versus this one where it's not possible. We'll start with the 3 examples on this page. Notice this matrix is 2 by 3, 2 rows, 3 columns. This matrix is 2 by 3. And the problem is the row length on this one, this 3, does not match the column length on this one, that 2. So the fact that this 3 and this 2 are different numbers, that's what makes it impossible to multiply these. If I go back to our previous example, this one is 3 by 2, this one is 2 by 3, and these inner dimensions match up. That's the important thing for multiplying. This one was 2 by 3, and this matrix was 3 by 2. 2 rows, 3 columns, 3 rows, 2 columns. The inner numbers match up, so it is possible to multiply these matrices. Let's go back to our simpler examples, where we did have some matrices that were pretty different in size. Let's see, this one is 1 row by 3 columns. This is 3 rows by 2 columns. Remember, it's just the inner dimensions that have to match up. Let's go back to this one, 1 by 3 and 3 by 1. Yes, the inner dimensions match up. And on our very first example, we had a 1 by 2 times a 2 by 1. The inner dimensions matched up. So we don't have to have outer dimensions that match up. All we have to have is inner dimensions that match up. But does that mean that the outer dimensions are not important at all? Actually, I think there is something to these outer dimensions. Notice the outer dimensions on this one are 3 and 3, and our answer is 3 by 3. Oh, did you notice that? And these outer dimensions are 2 and 2, and our answer is 2 by 2. We go back to our earlier examples. This answer was 1 by 1, exactly what those outer dimensions are. This answer was 1 by 1, exactly the outer dimensions, and this answer was 1 by 2, exactly those outer dimensions. So when we are multiplying matrices, we want to check those inner dimensions to make sure they match. And if we look at the outer dimensions, it tells us how big to make our answer. That's how I knew on this answer here to make a really big matrix where I could fit a 3 by 3 grid of numbers in here. I got to fit 9 numbers in there. So now that we know a little bit about multiplication, we're going to try and answer an interesting question here. The question is, can you multiply a matrix A by a different matrix and still get A as the answer? And the question is, what would that matrix look like? So I want a matrix A and something I can multiply it by, and I still want my answer to be A. Well, natural guess might be to put the matrix just filled with 1s. Because when we multiply by 1, we tend to get the same thing we started with. Well, let's see if that works. When I do the row times the column here, I get 2 plus 8. Wait a minute, that's 10. And row times column, I'd get another 10 over here. And here I'd have 12 times 1 and negative 3 times 1. So 12 minus 3, that would give me a 9 here. I don't think this answer matrix is the same as the matrix we started with. I could tell right away because I don't have the same number in the upper left position. So it must not be 1, 1, and 1, 1. So where did I run into a problem here? I multiplied 2 times 1 and 8 times 1. I think I would have been better off if I had just stuck with 2 times 1. That would have given me the correct number up in this position. But what could I multiply the 8 by so that it wouldn't show up here? Maybe 8 times a 0. So maybe if I put a 0 down here, then I could at least get this first position to come out right. 2 times 1 and 8 times 0. So it turns out I don't want a matrix completely filled with ones. I actually want a matrix that looks like this. 1, 0, 0, 1. 2 times 1 and 8 times 0 gets me a 2 in that upper left position. 2 times 0 and 8 times 1 gives me an 8 in the upper right position. 12 times 1 and negative 3 times 0 gives me 12 in this position. 12 times 0 and negative 3 times 1 gives me negative 3 in the final position. So this matrix is the one that acts like a number 1 for normal numbers. We call this thing the identity matrix. And we could write an identity matrix for larger matrices as well. If I want to multiply a 3 by 3 matrix by something and still get the same 3 by 3 matrix I started with, we would use the following identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. That's a 3 by 3 identity matrix. Here's a 4 by 4 identity matrix. Notice all zeros except for this little stair-step pattern of ones. You might recognize this pattern from the last video that we did when we did the RREF method of solving a system of equations. We came out with this pattern on the left, and then we had a column of numbers on the right that was the answer. But this is now called the identity matrix. And an identity matrix is always a square matrix, and we can make an identity matrix as big as we want to. Well, that's it for the basic matrix operations. We've learned addition and scalar multiplication and multiplication of matrices. Now, matrix multiplication can actually be done on a calculator, and for very large matrices, that's probably a much more efficient way to do it. For addition and scalar multiplication, you can probably do those kind of calculations in your head, or if you have to, get out a piece of paper. It's a little quicker than trying to put the whole matrix into a calculator and do multiplication. But for matrix multiplication, just put 2 matrices into your calculator and multiply one matrix times the other matrix. There is no such thing as matrix division, by the way. Instead, we would multiply by something we call the inverse matrix, but that's something that you'll have to learn in a future math class. That's it for this section, so go try and do some matrix operations, and I'll see you next time.